So last time we finished this slide, we talked about what is UTP, right? Unshielded twisted pair. And then we talked about CATs. CAT 6 is what is today available for very reasonable prices. CAT 7 is very expensive. CAT 5 is very cheap. Okay, so no, but this question depends upon how much cheap we want to go. I would do CAT 6 because you see, right now we have 10 megabit, and then tomorrow we will have 100 megabit. We have 100 megabit, right? We have gigabit right now in our offices. We will have 10 gigabit and 100 gigabits and so on and so forth. So the wire will become old very fast, or out of date very fast. So today, if you are wiring a building, particularly I'm talking about wiring an office building, you would not wire anything less than CAT 6. Yeah, so the Ethernet cable, for example, here's the Ethernet cable. I keep showing this one here somewhere. You never know what CAT it is. Only thing you is to show on the box. Once it comes out of the box, all bets are off. It might say on the wire itself, I don't know, but I really don't know a way of figuring out the CAT after it comes out of the box. When I buy it, they tell me, what price it is and what category it is, and then that's it. Once it comes and then I open the box, that's it. It might say on the wire, but there is so much writing on the wire, I never read them, but there might be something. So CAT 6 is the one which is today, and CAT 3 is your phone wire, and the CAT 5, 6, 7 are all the Ethernet wires. Other wires that are used for communications are coaxial cable. Now coaxial cable you have seen, if you have any dish network or any cable network, anything that uses, they use thick cable, right? Black cable. Actually it doesn't have to be black, it could be white. So the thing is, that cable has only two wires, one central metal piece, and then the seat, which is wire mesh, right? That is called coaxial cable, and in between there is a lot of insulating material and all that. So this one is very well protected in the sense that this doesn't radiate like the Ethernet cable, and it has very high, let's say frequency capability, so you can send a lot of data. So if you really wanted to send very high speed thing, that's why we use it for video. Video requires a lot more capability than the other things. So it can go up to 500 megahertz, and it is used in cable TV. We don't really use it for data communication, because as the time goes by, we are able to do more and more bits right in the unshielded twisted pair UTP, so we don't need to worry about this kind of cable. Now the next method is optical communication, and I start this cartoon that we are not the first one. Human beings are not the first one to use the optical communication. It has been being used since the beginning of time by fireflies for a very useful purpose. Basically when you see fireflies, they are actually optically, their signals are not random. All right, they use something called pulse width modulation. The width of the pulse says something, and so with that, let's go as to how do we do it now. So we discovered optical communication just few decades ago, maybe, and the way we do it is that we use an optical fiber. An optical fiber is nothing but a mirror. It's a cylindrical mirror. So it's a cylinder. This is glass. This is glass. This middle thing is a glass, and there is another glass. So there are two types of glass. There is a core and there is a cladding. And the light, when it goes and it falls on the cladding, it reflects, and then it reflects again, and it reflects again, and it reflects again, and then it goes there. So that's how the light travels, by reflection inside a cylindrical mirror. But it is such a good quality glass that not much of the light is lost, and it can go many, many kilometers without too much loss. Like a normal mirror, if you take the one that we use every day, if you put 4 or 5 mirrors, the light is gone, right? But here, after millions of reflections, light continues. So it's a cylindrical mirror. Actually, so there is a core, there is a cladding, and then there is something, there is a jacket, which is simply this plastic thing, so that you don't basically get into the glass. But basically that's it. So there is a two types, core and the cladding. And the light is propagated by reflection, not affected by external interference. The good thing is that nothing can get into this. So if you send something, that is the only thing that gets out. There is no reflection, there is no antenna, there is no interference from outside. If you have a lathe machine going next to your wire or fiber, nothing happens. But if you have a lathe machine going next to your Ethernet, the TV picture flickers. There is no interference. Fiber is used in all long haul or high speed communication. So whenever you want to go very long distance, we use fiber. For example, all international communication is by fiber. And so there is fiber under the sea between the countries. And all long distance means even between the cities. So from St. Louis to Kansas City, we will be using fiber. Copper doesn't go very far. Okay? So after a few kilometers, we start using fiber. And infrared light is used. So have you seen infrared light? Anybody has seen infrared light? Every day when you use a remote control which looks red is infrared. Right? Yesterday, in the last class, we had talked about the spectrum. So infrared is just before the red. Right? So most of the optical communication uses that infrared spectrum. All right. So wireless. Now, if you remember that electromagnetic spectrum thing, you remember that wireless was somewhere in the middle, and that middle is 2 to 60 gigahertz. I think book says something like 2 to 10 or something, but I have changed to 60 here because there is a lot of activity going on in 60 gigahertz right now. And so the book is actually 2006 or 7. It might have been written 2 or 3 years before that. In the last 5 years, 60 gigahertz has gone up. Basically in lot in activity. So that's the right number. And so that could be terrestrial microwave or satellite microwave. So many of you have seen the satellite dishes on the top of the buildings. They are pointing to satellites, very long distance. I don't know how many thousand kilometers. They use microwave. But anybody remembers what is a microwave? That was a spectrum that was shown earlier in the picture. This is microwave from 1 meter to 100 micrometer. 1 meter, 100 micrometer. That is microwave. So that spectrum, which goes from almost something less than a gig to 1 terahertz. That is most of the spectrum that we use in the wireless communication. Just like light, this is highly directional. So if you point your antenna this way, it goes there, just like the light. Actually what happens is, more higher spectrum, more you go in this direction, more directional it becomes. So this is light, and so the light cannot go behind a building. So if you have a sun, you go behind the building, there is no sun, right? But as you go away from here, lower frequencies, they are not straight lights. They can go behind, and depending upon the building size and the frequency that you're using, and the wavelength actually. So these things can go behind, but they are mostly going in directional. So basically, you can point antennas, and in high-speed communication that we do in wireless. By the way, I teach a course on wireless, and that's my area of research as well. So if you use wireless communication, then if you want to get long distance or something, then you point your antennas into the right direction. Just like you can point a flashlight, you can point an antenna, and you will get a lot more signal with directional antennas than without directional antennas. And they can be made point to point as well as point to multi-point actually. So this is, I would change that to both. See, one thing about the wireless is that it is, while it is highly directional, you could make it non-directional, and you could just light up the whole area in all directions. All right, then, so this is 2 gigahertz onwards. If you go down in the frequency, yeah, okay, so that's what they're trying to say in the book, is that if you go down in the frequency, then it becomes omnidirectional, and that becomes broadcast radio. So most of the television and radio that is transmitted today uses that frequency, below 1 gigahertz. Because in that band it goes in all directions, and it goes actually much farther as well. And then very high frequency is light, and so this is not really used. I mean, like, okay, here's the thing though. I mean, like, we talked about optical communication, but that can be called wireless because there's no wire. But I would put that as optical communication separately. But anyway, if you use this frequency, then you're using infrared, and you cannot go very far, and that's why your remote control does not go very far. When you use a TV remote control, it is limited to few meters there, unless you use it in fiber, in which case it can go kilometers. But in the open air, it cannot go very far. All right, so much about the media. Now we are going to change the whole topic. So let's just summarize the media. So we talked about wires, shielded and unshielded. Unshielded, we talked about different categories. Then we talked about optical, fiber, and then we talked about wireless, right? And so these are the three kinds of media, right? Now we go into multiplexing. Regardless of what media you have, if you have one wire between two cities, many people are going to share that wire. Or what media? It doesn't have to be wire, even wireless, many people are going to share that link. So how do they share? That is called multiplexing. So one way is to time share. So first the user 1 sends something, then user 2 sends something, then user 3 sends something, 4, 5, 6, 7, 8. This would be called time division multiplexing, TDM. Or you could frequency share. So I could use all the time, but I will keep myself in this frequency range, and second person could use that frequency range, third person could use that frequency range, and so on and so forth. That is called frequency division multiplexing. When you are doing cell phone, what are you doing? Time division or frequency division? Yeah, right. Actually, it turns out you do both. But initially, when the cell phone started, there was frequency division multiplexing, and now today we do both. Except that the time division is so fast that you really don't know that you are getting only 1 microsecond out of a minute or of a second. Because what they do is they take all your bits collected and then they send it in one burst. So you feel like you're getting all the time, because you're talking all the time, but the information is being sent in both combination of TDM and FDM. So each of these things is slotted in time as well. And that's how basically the capacity of the cell phone has gone up. In the beginning, when the cell phone came around, I remember 1980s, basically you could not have that many cell phones in a city, because it was frequency division multiplexing, and there were only so many people could, be given the frequency. But today we do both. So even one frequency is being used by many, many people at the same time. And then there's third thing which I haven't talked about here, because the book doesn't talk about here at this point, is the space division multiplexing. Is that nowadays, if you are using the frequency at this time here, I could have somebody else use the same frequency at this time here, directional. Right, so space, so in a single city the same frequency could be used at many places. So that's how we can put more and more people on wireless, or even on the wire, same for the same medium. So summary is there are two different ways of multiplexing, TDM and FDM. Now types of networks. This is historical again, I think. I don't know, I have kept this slide, probably I should not, but anyway. So the thing is, the networks could be point to point, or they could be a bus, they could be a star. 20 or 30 years ago there was a big debate whether bus is better than the star, but today there is no debate. Basically there are two kinds of networks today, this or that. Point to point, when you go wide area networking, when you go from city to city, it is like this. It's just any basically point to point connection. But when you're buying a building, it is always a star. So every port, if you have ports on a building, they all go to one closet. Single closet. That's a star. Outbreak bus, yeah. Because bus was very difficult to maintain and very difficult to find out where the problem is. With this one, you can just suppose you find out that the problem is somewhere, this guy is having a problem, you just remove him and the rest of the people can work. And then you can work on the repairing. So it's much more easy to maintain. So in the beginning, actually, Ethernet was the one that was bus oriented, token ring was star oriented, but today Ethernet is star oriented. All the Ethernet wires go to the closet. Point to point, which are not wireless networks. You mean this one? This is wired. So I mean, this is any general network. You know, if you're going from city to city, they have laid down some fibers, and wherever there is a fiber, there is a link. Wherever there is no fiber, there is no link. Okay, that's a different question. Let me set the question and then put a different answer to that. So his question is, can you use a crossover Cat5 to connect two computers? I would answer that question when we talk about Ethernet. Right now, I haven't talked about Ethernet. I haven't talked about what is a crossover. So it's too early to talk about. Yes, you can use crossover to connect two Ethernets. But, so that is your answer. But why that is and what that is, we'll tell you later on. Yeah.
So let's say these power strips that we have along here, actually you can plug in Ethernet. Wouldn't that be a bus though? Because we're all plugging in to...
Power strip? No. What you are plugging in is to a switch. And switch is exactly that. Old days we used to have a hub. That was more like a bus where everybody could listen to everybody. Today we have switches which basically you can't even listen to somebody. Suppose A is talking to B, C cannot listen to that because everything comes to the switch. Switch is smart enough to figure out which packet is going where and then only send there. So it's 100% that star. So the question is, are the switch point to point? If you think about this link, it is point to point. These are all point to point links. But the topology is a star. You understand? So these are all point to point. So the link is point to point, but the topology of the network is a star or a bus. That's what we are talking about. Alright, so having done that, now let's talk about whether it is circuit switched or packet switched. So in the old days, when the telephone company was in charge, when you made a phone call, they reserved a wire for you. So they used to have switches in the phone company's switching center, where when somebody made a call, they figured out that the call has to go through this switching center, and then the switches will move and they connect the wire to some other wire, and that will connect to some other wires, and you will have a completely physical wire connection between two people. Or there used to be an operator who would plug in and connect you. So the question is, can you define what is switching? Now that's a technical question. I will give you two answers. One answer for today and one answer when we come to the discussion between switching and routing. Then it is much more technical. But today, whenever basically you want to send information from here to there, you go through some device and you go from port 1 and come out of port 2. That is what we are calling switching today. All right. So there is more complicated information because router does the same thing. You send the packets through one and comes out to the other, and we call it routing. But that is because I haven't defined what is routing and what is switching. So right now for today's use, when we say switching, and actually I was talking about the telecommunication circuit switching. Okay, hold on. Okay, all right. So one more time. So there are two things we can switch. So what the telephone company was, actually you came a little bit too earlier than what I was defining. So let me finish defining and maybe it will answer your question. So what telephone company was doing, they had a circuit and they used to connect the circuit to another circuit to another circuit to another circuit, and you have a whole circuit switched, and then when you spoke, every bit went along that wire, and they didn't need any packets, they didn't need any addresses, nothing. So that was circuit switching. Today the way we do information exchange or even phone call is that you have the information and as packets, and the packets have the addresses on them, right? Everybody has an address. You have an address, I have an address, and as the packets go, the routers look at this address and say, okay, it has to go that way, they send that packet this way, this packet has to go that way. So today it is what we call packet switching. Today what we call is packet switching. Previously it was circuit switching. In circuit switching, there are no packets. No, there is no manual or automation issue here. Everything is automated today. There are circuit switching today also. So circuit switching can be automated. And packet switching is obviously automated. So circuit switching means that basically, like, he explained that in circuit switching you have to set up the circuit before you can send the first bit. That takes some time. But once the circuit is set up, your bits go very fast and they go along the path that was set up. And so that is circuit switching. Packet switching is where you don't, you could set up a circuit, but basically you don't have to set up the circuit. You could just send the packet. So it goes very fast. I mean, it starts very fast, but then every place people have to look it up and worry about it. So packets are like this, and circuit is shown like that, where this is a blue circuit, this is a green circuit, this is a black circuit. So there are many circuits here, and the information is going in parallel, but the circuits have been set up. And this is packet switching, where they're just different packets. So packet basically is a set of bits. Let's say we generally use 512 bytes. So that many bits we take together, and then we put the address and everything else on the packet, in front of the packet, and then we give it to the router. Okay? And then the router sends it around. So there is more technical discussion that we will have later on, but right now, for now at least, the switching means moving the information around, basically, from one port to the next. All right. So the main difference is that circuit switching requires call setup. In packet switching, you don't have to have a call setup. So there is a way where you could, even in packet switching, you could tell that I really want to watch this movie for the next 3 hours, so please reserve this much capacity for me to the router. So, but that is not generally done. So you could have, this is optional. Overhead during the call is minimal, because now there are no address bits, there is nothing else in this case in circuit switching, so there is no overhead during the call. In this case, every packet has an overhead. Stateful. What is a state? So in the circuit switching, the switches have to remember that this circuit is coming from A and going to B. If that switch died in the middle of this conversation, when the next switch comes up, it will not know what to do with this call coming from A. So that is called the state. That means there is some information that has to be remembered for this thing to function, and that state can be lost if the device that had the state is lost. On the other hand, in packet switching, if a packet is going from A to B, the router looks at the packet and says, I have to send it to B, and if that router dies, and then the new router comes in, then what happens? When they get a packet from A to B, do they have to remember anything? No. They just have to basically send the packet to B. So there is no state. And so the current internet actually is designed to be what we call stateless. So the routers don't remember anything. They can come up and down anytime they want. And believe it or not, that was the main reason why we invented switching, packet switching or computer networking or data networking, is because AT&T was the single point of failure. They were afraid in those days that Russia could invade USA anytime by putting a bomb on AT&T and be done with it. Right? Then we won't have any communication. But with the routers, they would not be able to do that, because with the router, they could kill one router, they could kill second router, they could kill 10 routers, but we could bring up 10 more right away and nothing happens. It's foolproof, it's fault tolerant. So that was the whole reason. Now it is used for very different reasons. But so packet switching has no state. Resource reservation is easy, but if you want something reserved, it is much easier to reserve on a circuit than on a packet basis, because that means remembering something which is difficult. Quality of service is same thing, is that basically you want to say, well, I want packets to be coming in 5 microseconds, so you want a delay guarantee. Or I want 10 megabit to be given to me all the time, you want a throughput guarantee. That is called quality of service. That quality of service is very easy to do on circuit switching, very difficult to do on packet switching. Sharing is very easy on packet switching. slightly difficult on circuit switching. Now, I think that is also they are different from the book, because book says that you cannot do sharing, or it says something like that. But it is possible to share here. So, for example, overbooking is what is done in the phone company or in airlines also, is that if they have 100 wires or 100 wires capacity, they could give service to 200 people, right? Because not everybody is using all the time everything, right? So they could do overbooking. Same thing as the airlines do. When they have 100 seats on a plane, they sell 110 tickets because 10 people will not show up, and they are fine, and they got 110 people's money, and so they always overbook. All right. The question is, frequency FDM and TDM, do they apply to circuit switching and to packet switching? The answer is packet switching by design is actually time division multiplexing, but and so obviously FDM and TDM apply to circuit switching for sure. For packet switching also they apply, because when you do packet switching and you have certain wavelength, say Wi-Fi, you're using Wi-Fi, then you decide how to send these packets. Who can send the packet? So you have packet to send and you have packet to send, then we could do time division multiplexing, or we could do frequency division multiplexing. So both of them apply to both. Hold on. So this is totally orthogonal. If you do a strict, if you hear a thing, overbooking is required because people do not use TDM. Suppose you have TDM, right? And I gave you a slot number 3, and you are going to use only, you don't speak all the time, by the way. When you're using phone conversation, you're using 50% of the time you're talking, right? Unless, something else happens. So 50% of the time you're listening, hopefully. And so 50% of the slots that are assigned to you for talking are going to go waste. So we could put 2 people on the same slot. So this is actually slightly different from the book. The book says that circuit switches requires dedicated resources and there is no sharing, but this is not true. Actually true only for CBR circuits. So there are circuits which are called constant bitrate circuit, where you are guaranteed constant bitrate, but there are many variations of circuit switching, and so this is actually does not apply to if you don't have circuit switching. So that's why I have put that in blue, just to make sure that you don't get confused between what book says and what I'm saying. And the problem is that many of such statements we differ from the authors, because first of all the world is evolving and the books are dated. Second thing is that people have different beliefs. Okay, some people believe in circuit switching and they will pro circuit switching, and some people don't believe in circuit switching and they will just write everything that is negative. So in that sense, there is no common truth. There is no common belief that everybody says, yeah, this is right. Okay, so from that point of view, from my point of view, circuit switching can be shared, and circuit switching does not require dedicated resources. The question is, should you not underbook? The answer is, if you want strict guarantees, suppose you said I want guarantee 1 megabit, and then I should be able to get it anytime I want 1 megabit. Then obviously I would give you 1 megabit, and there's no reason for underbooking. I could just give you 1 megabit and 1 megabit to 10 people because I have 10 megabit. All right. So that is what we will do. But the usage is so bursty. So usage of your DSL circuit at home is 2%. That means that 98% of the time you are not using it, right? It would be waste of, so what happens is the phone company gives the same capacity to 50 people, because 2% you are using, 2% they are using. It still comes out 100%, they get 50 times more money. At the same time, you are saving 50 times less money because you are paying 50 times less. Otherwise, they would charge you a lot. So if you want a guaranteed 1.5 megabit all the time, you pay a lot more than if you want 1.5 megabits shared, where you get 1.5 megabit when you need it, but when you don't need it, somebody else can use it. So that is what overbooking is all about. Overbooking is about giving the resources to somebody else when you are not using it. It's the same thing in the airlines. They sell more tickets, and hopefully people will not show up. If some show up, then they give you extra money to get off. right? And if they didn't sell that 10% extra ticket, everybody has to pay 10% more. So now we go to a totally different, now this is actually much of an overview lecture, so it goes all over. So the next thing is what kind of networks we have. So there are two kinds of networks, enterprise and telecom. They are very different. Enterprise is WASU network. Any company, any university, they are all enterprises. Telecom is AT&T, Verizon, Sprint. They are telephone companies. They don't call them telephone anymore because they are not in the phone business. They don't make any money out of voice. They make more money out of data. When you have a cell phone, they make less money out of your phone than from the data plan, right? Data is where the money is. So they call themselves telecom companies. And so their networks are very different. They were actually much more different before, but they are becoming now similar. So they are adapting. So nowadays it is not very different, but still they are in the business of providing services to other people, whereas enterprises are in the business of using it for themselves. So the networks are different. So Ethernet is used actually mostly in enterprise. Frame relay is used mostly in telecom. So there are some protocols which are different. Now you don't know what frame relay, so it doesn't really matter. But the idea is that the telecom companies have some protocols that are not used in the enterprise, and the enterprise has some protocols that are not used in the telecom. Second difference would be the distance they go. So we have protocols that go only short distance. We call them local area network. And there are protocols that go long distance. We call them metropolitan area networks. And then some that go very long distance called wide area networks. Well, that was original definition of LAN, MAN, and WAN. Now they're all the same, except that the ownership. LANs are owned by one organization. MANs are generally owned by the phone company and shared by many organizations, and WANs are owned by the phone company too. So they are more about the ownership than about the distance. Because Ethernet can go, previously, 10 years ago, when we used to teach the same course, we used to say Ethernet is a LAN technology. Today it is not. Today Ethernet is used even for MANs and for WANs. But that Ethernet which is used for WAN is owned by the phone company. The Ethernet that is used for LAN is owned by the organization, by the company owning it. For example, WASU or your own home, you have Ethernet, you own that Ethernet. But the Ethernet which comes from the phone company or which phone company uses is for everybody else. So the question is, what is Ethernet? I keep saying this cable is not Ethernet. That cable is simply a cable. On that cable I can send anything I want. I can send Ethernet. Ethernet is a protocol. Right? I can send any kind of message on that cable. So we keep calling it Ethernet cable, but that is not really nothing to do with Ethernet. It's just a cable. I could be sending token ring protocol on that one. Alright, so Ethernet can go on fiber, Ethernet can go on that cable. And Ethernet can go on some other cables as well. So that was the confusion you had. The question was, can Ethernet go on fiber? Yes. We haven't defined what Ethernet is. Ethernet is a protocol, which we have not defined yet. But I have been calling that cable as Ethernet cable because that is what most of you are familiar with. Right? I mean, when I say plug in your Ethernet, you just plug in that cable, and this so happens that nowadays we don't have any other kind of cables, any other kind of protocols. In our days, in old days, we had Ethernet, token ring, and different kinds of, many more variety. All of those have gone. All right, now the war has been settled in favor of Ethernet. So there is only one protocol. In fact, so that is the reason now. Anyway, so the idea is, Ethernet originally was, as I said, was a local area protocol, but now it is used everywhere. But they are different because of the ownership. The telecom networks, the telephone networks are also of different kinds. So the enterprise network is the network inside. So in WASU, they have lots of switches in the closets and lots of wireless transmission. These all belong to WASU. That is the enterprise network. But then they are connected to AT&T at some place. Right? So that is where they get the internet from, is that, they are connected through the telecom company. Question is, all the frame relay and ATM are also protocol? Yes, Ethernet is a protocol. I gave an example here up to a protocol which is used in enterprise and a protocol which is used in telecom. And these are not really used in enterprise at all. We don't have frame relay in WashU. Alright, so let me go back to the last point. The telecom networks can be of three types: access, metro, and core. Access is the part of the telecom network that goes to the user, to the homes, to the offices. So the telephone company wire that goes, AT&T wire that goes from their switching office to your home, that is access network. The wire that goes between the switching offices is different, or may use different protocols. That could be one of the two types, either metro or core. Metro is the one that goes around the city, and the core is which goes between the cities, just like MAN, WAN, and LAN. Right? So the telecom networks are access networks, metro networks, and core networks. So one of the access technology, most popular access technology is, for example, if you go to AT&T and you say, I want 2 megabits, what kind of technology do you get? What is that service called? DSL. That's not Ethernet, by the way. DSL, that's the protocol too, right? So the idea is DSL is the access technology. That is not used in the metro or core. It's just used in the access. More and more. So the thing is, there are other technologies that they used to use before. Now they're adopting Ethernet for metro and wide area.
Instead of frame relay and ATM.
Yeah, instead of frame relay and ATM. Yeah. And tomorrow, I would not be surprised if you started getting pure Ethernet on the access as well. Right now I said DSL, right? Now the DSL today is actually, believe it or not, is ATM based. So when you get a DSL wire, you get ATM cells to your home, and then they put a device which converts that into Ethernet. Right? That's why you need that modem, DSL modem, which converts ATM cells to Ethernet packets. But Ethernet is not coming from the phone company. It is just starting from that modem. ATM is actually just like packets, but it's a different technology. Instead of packets, they use fixed size packets. And I think that should be sufficient for now, because there is, we are going to discuss ATM later on, more detail. But right now, all these terms are coming in because I have to use examples. We haven't even defined, for example, what is Ethernet, but we are using Ethernet because everybody knows. So ATM is actually a packet-based telecom thing where they use a 53-byte packet, fixed size packet, as opposed to a normal packet which are generally much larger and much more variable. All right. So the ATMs are like packets, but they are fixed size. All right. That brings us to homework number 1A. And so you need to answer 3 questions. Which network media will you use for the following applications and why? Very large file transfer at home, high-speed multiple channel video transmission at office, and news reading while traveling in a car. I think these are all very trivial questions, and probably you all know the answer, but you just write it down. Make sure that you read chapter 1 up to at least this far before answering these questions. By networking media, I mean one of those 4 or 5 things we talked about here. STP, UTP, and coax, and optical fiber, and wireless.